Let's now look at a couple of discrete probability distributions that come from a mathematical formula. So the first we'll look at are binomial and hypergeometric, but both of them make use of this idea of counting rule that we discussed earlier, that of combination. So again, just to recall, remember that NCX gives us in how many ways can we draw a group of X from a set of N outcomes or N objects. And it's given by N factorial divided by X factorial N minus X factorial. And recall that N factorial is just N times N minus 1 times N minus 2 all the way to 1. So this is just the product of successively decreasing values from N onwards. So we'll make use of this in the next two distribution functions. So the first one we look at is hypergeometric distribution. So to best understand hypergeometric distribution, let's use an example and then see how that example fits into what requirements for hypergeometric distribution are. So let's say that from a deck of cards, you're drawing 5 cards, and we want to know the probability of getting exactly 2 aces from those 5 cards. Now, if we are drawing a hand of 5, there are a total of 4 aces, and we want to look at the probability of getting 2 aces out of those 4 aces. And then again, we are drawing a hand of 5, so we are left with 3, and we don't care about what those other 3 cards are and how many cards then will that be possible from. Again, we don't want any more aces, so we can subtract the number of aces we get in a deck. So 52 minus 4 would be 48. So in the first instance, we are looking at probability of getting 2 aces from 4 aces, and then from the remaining 48 cards, getting any 3 that we don't care about. So to get the first probability, again, it's NC4, which is 6. So there are 6 ways in which from a set of 4 aces, you can get 2 aces. Again, the sequence does not matter. And then for the rest of the cards in the hand, out of a 48 possible cards, we can draw any 3, and that's given by 48C3, which is 17,296. Now, these tell us the possibilities of drawing those hands, but then we have to divide it by how many ways can we draw a hand of 5 from a deck of cards. So the denominator is 52C5, and the probability of that is 0.0399. So in general, the hypergeometric distribution is given by this function where A is in how many ways can an outcome be successful, and the exact number of successful outcomes is given by X. So A is your successes, and X is how many successes do you draw from. And then the other option is the failures. So if we have A successes, then N minus A are our failures. And then we are drawing N events. So small n minus X would be the remaining events. So the 3 key properties for a variable to be a hypergeometric distribution would be that the population should be divisible in only 2 groups. So in our example, we said aces and everything else. So our capital A in that case was 4. We could get 4 possible aces. Our number of draws in a hand we said was 5, and we are counting success as getting exactly 2 aces from our hand. So that's the first thing, that we should be able to divide population in 2 distinct categories. And then the second important thing here is that the experiment must have changing probabilities of success with each trial. So here, when we were drawing cards, we were doing it without replacement. So the moment we draw a card and set it aside, it alters probability of the next draw. So it was a successively changing probability. And again, the outcomes must be discrete. So we cannot work on this with the continuous case. So if we have these three properties or conditions met, then the probability distribution function of such a random variable can be classified with the hypergeometric function. Again, we can do these calculations. Once we have our capital A, our N, our X, we can pretty much calculate anything on this distribution. Another important distribution is binomial probability distribution. Now, this is kind of like hypergeometric. We have successes and failures, but the key difference here is that our probability of success does not change with each trial. So each trial is independent of the past trial. The result of that one trial has no bearing on what happens next. And then, so think of this as drawing with realism. Let's say that you have a hat with 40 balls, 10 are red, and 30 are green. And you draw 5 balls, but every time you draw a ball, you put that ball back, and so you're drawing again. So let's say, then we can calculate our probability of, let's say, our success with making 5 trials, getting 1, 2, 3, 4, or 5 green balls. So in this case, each trial is independent of the outcome of the previous trial. So that's an example of a binomial distribution. So let's say you're playing a game where the probability of winning is 0.6 and the probability of not winning or losing is 0.4. And you play this game 10 times. And each time that you play the game, these probabilities do not change. So this is an example of a binomial probability distribution. So in this case, the probability distribution function of such an experiment is given by this formula. Now, this formula is fairly easy to understand. It looks a little complicated, but again, we have independent trials. So let's say we are doing 10 trials, and suppose our success is 4 trials. We want to get 4 successes. So the probability of getting 4 successes in independent trials would be our probability of success to the power 4, because p times p times p times p. Then consequently, we're getting 6 failures. So probability of failure is 1 minus p, or q. And then we are getting 6 independent trials. So 1 minus p times 1 minus p, again 6 times. But now, because these can happen in any sequence, we don't care if we get 4 successes right away or we get the first success and then the second success after a gap. So the n combination x is kind of allowing that you can have them in any sequence, in any order. So this is the probability of getting x successes in n trials when the probability of success and failure does not change with each trial. And for a binomial distribution, its property is that its mean is the number of trials times the probability of success, and its variance is the number of trials times the probability of success times the probability of failure. So again, a pretty simple distribution. The formula looks complicated, but once we unpack what's going on, how to define a binomial experiment, it kind of makes intuitive sense. So let's work with a concrete example. As we said, our probability of success is 0.6, so which means 1 minus p. It's also sometimes called q, is 0.4, and let's say that our x is 3. So applying, this is a binomial event because the probability of our successes does not change with any trial, with successive trials. So plugging these in, we have 10c3, and then our p time to the power 0.3, and then 1 minus p, which is 1 minus 0.6, to the power 7, and when we do that, we get 0.042. So this is the probability of getting exactly 3 successes in doing n trials with these probabilities. Then we can also get the mean and the variance. Our mean is not n times p. Our n is 10. Our p is 0.6, so n times p would be 6. And then our variance would be 2.4. So again, our interest is in getting the probability of 3 successes out of 10 trials. But we'll kind of look at a general way in which we can do this in JMP. So there are multiple ways, but I want to show how to get a random variable following the binomial distribution with the given parameters that we have discussed. So let's just get an empty table in JMP. I'm going to call this table X, where X is our number of successes. And then let's just make a list of successes. We're doing 10 trials, so we could get up to 10 successes. So we can get up to 10 successes, and we will now create a new column in which we will first get our probabilities of each of those trials. We can also get cumulative probabilities if we wanted to. So we right click on the column that we just created. We click on formula. And JMP has just a variety of formulas that have been used to create columns. We are interested in probability, well, specifically discrete probability. So we'll click on discrete, and we're interested in a binomial distribution. So distribution is cumulative. We're interested in binomial probability. I'll show the difference between the two in just a little bit. So let's say we want to click on binomial probability. We want to know the probability of getting our given successes. Our P is 0.6. It will not change. And then N is the number of trials. Let's say we do 10 trials. And we could have typed in 4 for K. K is like our X, but I can just drag the column there, because now we will get 11 different probabilities for trials ranging from 0 all the way to 10. We click OK. And here we get the probabilities directly. We get the probabilities of all of these options. Again, we had calculated the probability of getting 3 successes of 0.042, which is what it is here. But then we get the probability of trials from 1 all the way to 10. And if we add this up, we will get the sum equal to 1, because we know the probability function's property is that we sum up all the probabilities of each of the outcomes possible. That should add up to 1. So we can call this our PDF, or probability distribution function. And then let's also look at the cumulative function. I'm going to double click on this column, formula, and this time we will choose the binomial distribution. And again, it gives us the cumulative probability of the binomial. So here, again, our P was 0.6. Our N is 10. And our success is given by X. I'm going to drag this down, click OK. And now we get the cumulative distribution as well. And it all adds up to 1. So it is basically adding up the probability with the last probability, and then so forth. This is the general way of getting any probability distribution, not just binomial. So just to illustrate again, we would apply this method whether we want to get any discrete, and JMP has all of these, including hypergeometric distribution that we had seen, as well as a variety of discrete distributions, and then it also has a variety of continuous distributions that we will examine later on. So this is how we can get the random variable following any given probability distribution for the number of parameters that we can specify. The last discrete probability distribution we'll look at is a Poisson probability distribution. Poisson distribution is used to find the probability of the number of times an event may occur in a given interval. So it is useful in a lot of business settings. For example, number of patients you may expect to come to an emergency room department given the prior data on how frequently patients have been coming in. So this variable essentially has just one parameter, mu, or its mean. Sometimes it's called the lambda as well. And then x is the event, the number of events of interest. So its probability looks a little scary, but we will unpack it. We will kind of do some calculations as well. So suppose the average rate is mu, and our number of successes is x. The probability is given by mu to the power x times e, which is the Euler's number, the natural number, to the power minus mu divided by x factorial. And this variable also has distribution, another interesting feature, that its variance is also the same as its mean. So let's apply this in a problem. Just to recap, our Poisson probability distribution function was given by mu to the power x, e minus mu, x factorial, where x is our number of success, and mu is the average rate of success in a given interval of time. So let's consider a problem where a customer service center receives 10 emails every half an hour, so every 30 minutes. What is the probability that the center receives more than 4 emails in the next 6 minutes? So again, a very practical question. I can apply this to an emergency room visit context, to any business waiting context, etc., where we're interested in finding out the number of events that occur in a given interval of time. Before we work with this, there are a couple of things to keep in mind. Our interval of interest is 6 minutes, but we're given data in a period of 30 minutes. So this 10 is not our mu or our lambda. Some softwares may call this as lambda. We are interested in first converting this 10 into the average rate in our period or interval of interest. So in 30 minutes, we're interested in 6-minute intervals. So there are 5 6-minute intervals in every 30 minutes. So this 10 will divide this by 5. So our mu is 2. So our average expected rate is 2. Now we want to find the probability of getting more than 4. So, but probability distributions are often given in terms of cumulative distributions, the probability of getting up to 4. And we'll make use of the second property of probability distribution function we looked at, that the summation of all probabilities equals 1. So the probability that our x is more than 4 is basically 1 minus the probability that our x is less than 4 or equal to 4. Now this is a discrete distribution, it's countable, which means it is 1 minus the probability our x equals 0 plus probability our x equals 1 plus probability our x equals 2, x equals 3, plus probability x equals 4. So we have to calculate all of these probabilities, add them up, and then subtract that from 1. Seems like a tall order, but again, each calculation will be done individually. So for example, if my x was 3, I would kind of plug this into my formula. It says mu to the power 3 e to the power minus 2, because our rate is 2. Again, our mu was 2, so I should have just written 2 here directly, divided by 3 factorial. So again, doing this 5 times gets a little unwieldy. Let's see how a software can do that for us. We will use JMP to do kind of these calculations. We want to calculate the probability of getting more than 4 emails. But this will be a little different than what we did for binomial, where we're able to list out the number of trials and then have our successes. The question doesn't ask us up to how many, it just says more than 4 emails. So we can, extend the series to as far as we want, but here we'll try to get a more direct answer. So I'm just going to type in 4, because we want to get our cumulative distribution up to 4, and then we can do 1 minus the cumulative distribution up to 4 to get the probability of getting more than 4 emails. So again, I'm going to just create a new column, right click, formula. So here, knowing the math and the properties of cumulative distribution function, probability functions is helpful. Instead of doing it in 2 steps, we can just kind of do 1 minus, because we're creating a formula. 1 minus what? 1 minus the distribution of up to 4. So I do 1, enter, and then I subtract, then subtract what? I want to subtract the cumulative distribution of Poisson up to 4. So we will choose Poisson, but this time we will use the distribution, not the probability, because we want to get up to 4 events. Lambda or mu, our expected value, our mu is 2. And we want it up to 4 successes or 4 emails. Again, this is cumulative, so this will look at 0, 1, 2, 3, and 4. We click OK. So what we now get is there's 1 minus the cumulative distribution. So the probability of getting more than 4 is 0.052. Or about 5.26%. So there is a 0.052 probability that this call center may get more than 4 emails in that 6-minute interval.